Now, with at least the beginnings of a systematic way of naming compounds in place for molecules, you'd think that when we start to talk about organic molecules would just, in general, be molecules containing carbon, that we could use the same set of rules. But no, chemists have not done that. In fact, a lot of the organic compounds have been known and had names long before some of the other compounds. So there is a bit of a different nomenclature system in place for organic molecules. So let's take a little time and see how that works. And again, what we're looking for here is not memorizing names, but more looking for patterns in those names. Now, if we look at a class of compounds called hydrocarbons, they are indeed compounds containing only hydrogen and carbon. And we look in particular at a class called alkanes, and we'll talk much more about alkanes later. But alkanes would be hydrocarbons, where the carbon has as many hydrogens as possible. So these are often referred to as saturated hydrocarbons. Now, we don't understand yet at all what that means or how we determine whether something is saturated or not. So don't worry about that yet. We will get there. Right now, I'm just describing this as a collection of molecules having a general formula. In fact, we could make some sense out of this, is if the number of carbons was n, the number of hydrogens would be 2n plus 2. So CH4, C2H6, C3H8. Now, I don't care about you knowing that formula yet. It doesn't mean anything to you, so what's the point? What I do want you to see is that the names all end in ANE in this class, and in particular, the number of carbons is dictated by the front end of the word. So methane indicates that it has one carbon. Methane comes from cows, so lots of methane from cows, lots of other places we get methane also, underground mostly. But again, a one-carbon hydrocarbon. Anytime you see that meth, that's telling you it's a one-carbon molecule or a one-carbon fragment connected to another part of the molecule. Anytime you see eth, on the other hand, like ethane, ethanol, ethene, we'll get into, that indicates that there is a two-carbon fragment, or that the molecule contains two carbons. So again, you'll notice the formula. We've got now two carbons. The next on the list would be pro for propane, or propanol, or isopropanol. Anytime you see PRO, that's telling you again that you've got now a total of three carbons, either again in a fragment or in the overall molecule. Next on the list, so propane you're familiar with from propane fuel, for instance, like you would use in camping stoves. Butane, like in butane lighter, if I can light it, there's a butane lighter. Butane is a hydrocarbon as well. It's a four-carbon containing hydrocarbon though. Pentane, as you might expect, is a five-carbon containing hydrocarbon. So again, we can go on to hexane, to decane, and so on. But right now, let's just focus on this first group of five, meth, eth, pro, bu, pent. Those are telling us, again, the number of carbons. So if we look at a related family of hydrocarbons, the alkenes, for instance, the alkenes sound very much like the alkanes, but notice the difference. If I look at ethane and ethene, the eth tells me, again, I've got two carbons. Look at the formula. But notice that I'm missing now two hydrogens. And in fact, for all of these cases, if I compare the alkene and the alkane, I'm just missing two more hydrogens here. This is referred to as a class of compounds that are unsaturated, meaning they could take additional hydrogens, and if we gave them additional hydrogens, we'd get alkanes. But right now, our focus is simply on how they're named. And again, the key is that both propane, for instance, and propene have three carbons, and that word, or that prefix pro, tells us, or that root I should say, tells us how many carbons we have. Thus, pentene would have five carbons in it. And notice again, all of these have an ene ending, indicating the type of family they belong to, the alkenes. A third family of hydrocarbons would be the alkynes. A different ending again, YNE. Fewer hydrogens still. Now notice for ethane ethene, and ethyne. We've gone from 6 hydrogens to 4 hydrogens to 2 hydrogens. And so, again, these are different compounds, but they share in common the fact that they have a total of 2 carbons. And that eth, again, is what tells us that. Now, once you understand that, once you start to recognize anytime you hear these different roots, that they're corresponding to simply the number of carbons, again, either in a fragment or in the molecule, you can start to make sense of some really pretty impressive words. You'll recognize these roots in all kinds of words in the ingredients. This thing contains isobutane, 4 carbons, if I can say 4. It contains propane, 3 carbons. It contains neodecanate, dec, 10 carbons in this case in that molecule. So a lot of information is embedded in these words once you start to associate meth, eth, prop, but, pent with the corresponding number of carbons. Let's look at one other class of compounds, and that would be the alcohols. Now, alcohols, much more in this family than just the type of alcohol that you're familiar with, the kind that you drink. That actually is ethanol. Eth right away tells us 2 carbons. All, the ending OL, that's going to end up telling us that this molecule has an O connected to a carbon and connected to a hydrogen. Now, we don't know the first thing about bonding yet, so we're not going to go into much detail about this, but we will begin to recognize that anything ending in an OL is in fact an alcohol, does in fact share a common piece of chemical structure, and therefore behaves actually chemically in a very similar manner. So ethanol and propanol, another example, in this case isopropanol, that's just rubbing alcohol. It is again an example of an alcohol. That's what that OL ending tells us. Prop tells us it's an overall 3 carbons, and so this is the chemical structure of propanol. Notice there are the 3 carbons, and here is the OH telling us that it's an alcohol. So again, we can pull out pieces at least of this. This prefix iso simply means that it's different than something else. It's different than propanol itself, or normal propanol, and that would have this OH stuck on the end of the carbon chain rather than in the middle. Not important. The important part is prop, telling us again 3 carbons. Estradiol, this is a female sex hormone. Do I have your attention now? Now, this guy is an ugly, huge molecule, but it is 2 alcohols, diol, and those are the 2 OH groups. So even in these big complex molecules, we can get information about chemical structure. Even if we don't understand everything about the molecule yet, we get little bits of information. And in fact, we'll find that chemically, estradiol acts very similarly in some ways to isopropanol or ethanol, in that they are all alcohols and undergo certain chemical reactions that are very similar. Obviously, there are big differences in these guys too. So for right now, let's just focus on these roots and what they mean, just committing to memory the idea that meth means 1 carbon, eth means 2 carbons, prop means 3 carbons, but means 4 carbons, and pent means 5 carbons. And there's many others, but these are certainly going to be the most common roots that you're going to need to understand to be able to make sense out of the names of organic compounds.